Okay, so basically yesterday you were seeing. No, let me ask you this question. What were you seeing yesterday? Somebody just summarize what was covered yesterday. Just in 2-3 lines. What was taught yesterday?
Properties of
Yesterday,
concrete.
what was? Yeah.
Properties of compressive strength of concrete, Mohr circles, and stress strain curves.
Okay. So one word, how you can say it? Yeah. So basically, you have seen all the properties of concrete. Okay. Properties of concrete and behavior of concrete in different conditions of stress. Okay. So that is what you had seen yesterday. So now the next, basically all those things were covered a bit for you in concrete technology itself. Okay, whatever was covered in the last class. So now for this course, it is basic reinforced concrete design, meaning that you're going to design reinforced concrete structural elements. So for doing this reinforced concrete design, what are the design philosophies that are there and which one you're going to use? So all these things, and what is the thinking behind these philosophies, all these things you'll be seeing now. Okay, so every design has to go according to some philosophy in engineering. So what are the things that decide what philosophy to use? Okay, so that's something that we'll see now. One is how simple the theory is. So the simpler the theory, the more keen people will be for using it. How much safety is inbuilt in the use of that theory? Okay, so what is the inherent safety in using a particular design philosophy? That is the second criterion. Third criterion is how economical with that design philosophy prove to be. Okay, so if you use a certain design philosophy and you do a design, you see that it is coming very expensive, then there is a drawback which will make people probably to not use that design philosophy. And in some cases, for specific uses, sometimes engineers would want to use a specific design philosophies. So, for example, for something that is very crucial, strategic importance, and which has to be protected even under severe circumstances. So, in such a cases, people may want engineers may want to use a design philosophy which has more safety without bothering about the economy. If it's a structure which is of common use, then the thinking would be, no, let us not waste too much money on it. Let us not be very extremely safe on it. Let us have some safety, but also let us make it economical. So the philosophy will differ based on what the utility will be. Then the degree of uncertainty, okay, things like external loads, etc., which may change from time to time. Those things also affect what is the design philosophy that will be chosen. Okay. For example, all these four things are for a particular purpose. Each is to protect against external contaminants. Okay, so now who uses what depends on many factors. For example, where are you going? Are you sick? Where do you work? Who are you meeting? And of course, how much money do you have? Okay. So depending on that, one person may decide to choose either a simple mask or a face shield or this PPE or a hazmat suit. Okay, depending on what they're going to do and where they're going and how much money they have. For example, these days, so the initial days of Corona, if you remember, anybody who traveled in anybody who traveled in trains, even they used to wear a face shield and go. Because in those days, the degree of uncertainty was quite large regarding how the infection spreads, etc. These days, because people are too casual, mostly people just use a face mask, and that too, sometimes they will just use it very casually. And of course, people who have more money will try to get PPEs. Back in September and all, when last September, if anybody boarded a flight, they would be given a PPE to wear. These days they're not given it because no, airlines also realize it's a waste of money because people don't bother to use PPs anymore for preventing infection. So money is also a matter. So the choice decision which you make is something which is a convergence of three different things. One is safety, one is simplicity, and the other one is the cost. So the one which the most optimal choice is the one which satisfies all three. Sometimes you may not be able to satisfy all three, so you may have to choose a design philosophy which takes care of only one thing or two things. Okay, so this is the rationale behind any design that somebody uses. So this is true even for doing steel design, concrete design, or any structural design. So the first design philosophy is known as your working stress method. Okay, so there are some features of this working stress method, and there's a which makes it to be one particular design philosophy. Okay, the name of that method is the working stress method. This method is it was common before 2000. Okay, the year 2000. Then after 2000, one more method which will come, which will be dealing more in this course. Now I will be talking about it from maybe next week. So before 2000, this method was more used, and even now in your IS 456, if you open your code book IS 456, you will not have working stress method in the main part of your code book. So you will have to go to the back of your code book where you have annexes, Annex A, Annex B, Annex C, etc. Data files will be there. In that one, only in the Annex B you will have working stress method. In the main part of the code book, working stress has been removed from IS 456 because this is an older method. But that does not mean working stress method is obsolete or it's not being used at all anymore. So still, even today, for some particular applications, working stress method is used. Okay, one of those things is, for example, a water tank. Okay, so what does this working stress say? So basically, you are permitted to work within a stress limit for doing your design. Okay, so what does this mean? So one thing is this working stress method is simpler. It's older, therefore it is simpler. So what it does is only the linear part of the material curve is used. Okay, so if you remember, do I have a picture? Yes. So if you remember in your yesterday, you saw this stress strain curve for concrete. Okay. Now, why is this equation used for the stress strain relation? What is the reason for this equation? I mean, what kind of an equation is this? Is it linear or what shape does this equation represent?
Parabolic.
It's parabolic. Okay. So almost entirely this curve cannot be called as a linear. It's not a straight line curve. Okay. It's not a linear stress strain relation for the entire range. However, probably if you take only a small part of the stress, for example, corresponding to this red color line. So within this part, probably it is somewhat linear. Okay, so I just zoom this over here. This part may be somewhat linear. So the working stress method, what it says is, use only the linear part of the material curve. So if the characteristic strength is this, use only 1/3 of it because only that part is linear. Okay. Why do you want to do it? Is because if it is linear, you can use something known as a transformed section, and you can use something known as a modular ratio. Now the word modular ratio. Did you have composite? What is it? Composite sections stress strain. Stresses in composite sections. Did you have that in your mechanics of solids last semester? Composite sections. I think you would have had. I think it is there in your syllabus. I think. Did you have composite sections? Mechanics of solids. Like for example, there is a brass tube inside. There is a steel tube. I mean, and it is being stretched. What is the stress in the steel? What is the stress in the brass? Now, these kind of problems did you come across last semester? Not last semester, last year.
Yes, sir. Like this, we have two metals.
You had, right? So So what do you do? Do you remember taking a ratio of the modulus of elasticity, modulus of elasticity of steel by modulus of elasticity of the other material? You will take a ratio. Do you remember all that? For finding the stresses, you will have one ratio of the Young's modulus. Do you remember or not remember?
Yes, sir, modular ratio.
Yeah, so if it's a linear, if you're taking only linear stress strain relation, it is possible to use a modular ratio. So therefore, it is simple to this working stress method simplifies by ignoring 2/3 of the stress. Only 1/3 of the stress is used. So therefore, what do you think? Is this working stress method? What is it? Is it economical or expensive? Only 1/3 of it. It's expensive because you can use it. You can use till if actual strength is FC or no characteristic strength, but working stress method says only use 1/3 of it. So it is expensive. But at the same time, because of that, it is highly restrictive. So therefore, the factor of safety is quite high. Because instead of assuming that concrete can take this much stress, you are assuming that it will take only this much. Okay, so it has safety, and economy wise, it is strictly speaking, it is actually expensive because you use only a very small part of the stress which can be used. Okay, but one thing is, in the olden days, almost everything was done using the working stress method. All those buildings, they have not really developed any problems. Okay, and because it is your initial cost may be high in many cases, but they last long. Okay, and of course, because you assume this linear relation between stress and strain, and you don't actually consider the whole thing, you lose a bit of accuracy. Okay, the linear part of the curve is set aside. Because of that, the working stress method loses a lot on the accuracy. But for most day-to-day structures like normal buildings, apartments, and common kind of structures, that level of accuracy is not really necessary. Okay, so this is the basic principle behind working stress method. Okay, you just use part of the stress, and this is known as the working stress. The stress limit which you set is known as the working stress. Okay, so now as I told you before, so you see over here this assumption plane sections. So mechanics of solids, Euler-Bernoulli beam theory. What is the first assumption that is made? Beam bending theory, mechanics of solids.
It's purely elastic.
Purely elastic. Okay, that's one thing. Then
the bending will be part of the.
Bending will be part of.
Like there will be a part of circle, like a curve, like the exact curve.
Okay, fine. Then one more, two more. Yeah, come on.
So it is like linear. Stress strain is linear.
Yeah, that he told already. Elastic and linear. Okay, fine. That is there.
It follows Hooke's law.
That is what is elastic and linear. No, follows Hooke's law. Okay, there's one.
For deformable body.
Huh?
For deformable body.
Yeah, it is for a deformable body. It's deformable motions. Okay, the assumption that most of you are forgetting is one of the main assumptions is this. If you recollect, there will be an assumption which says plane sections remain plane before and after bending. Okay, try to recollect that assumption. That is a very important assumption in that theory. Okay, so only when you have plane sections remain plane before and after bending, if you recollect, this is the shape of your stress strain stress across the depth, okay, of your beam. So I hope you have come across bending stress distribution. Top is compression, bottom is tension, and it will actually form two triangles. Do you remember this? This is how you people told yesterday, rightly so, that under normal bending circumstances, The top of your beam will have compressive stresses and the bottom will have tensile stresses. So this thing you knew, you told yesterday. So of course that means you have a neutral axis. So the way the compressive stress and the tensile stress, the way they are joined or the way they vary is through this triangle. Have you seen this before? Two triangles?
Yes, sir.
You've seen this, right? So this is one important thing. So because plane sections remain plane before and after bending, you can make this assumption. And now what we also say is, we know that no, in concrete tension is not taken very well. Okay, it's pretty poor in taking tension. So in the working stress method, what they do is, if you have a concrete beam, so always say that this whole thing, breadth B and depth D plus, I'll come to later what is the meaning of this effective cover. So just assume that it is B breadth and D depth. Usually your reinforcement, a conceptual question that I'll ask you now is, where do you want to keep your reinforcement? Do you want to keep it where the compression stresses, or where do you want to keep it where the tension stresses? Where do you want to keep the compression and why? Where do you want to keep the reinforcement and why? By the way, anybody who answers, please tell me your name and answer so that I know who is answering.
Sir, Varun.
Okay.
We have to put the reinforcement in the tension side to take the tensile forces, as the concrete is weak in taking tension.
Yeah, so concrete is weak in tension. So in order to aid that tension carrying capacity, you place the reinforcement at the bottom. So what they do is, in working stress method, they identify the neutral axis. Because this is a composite section, it's not homogeneous. So therefore your neutral axis will not be at the middle. It will be somewhere either below the middle or above the middle, depending on how much reinforcement you have. If it's a homogeneous beam like steel or something else, usually neutral axis will be right at the middle. Okay, here it's not the case. So the whole depth may be divided as KD and D minus KD, etc. And because concrete does not take tension very well, in the working stress method, you assume that there is no concrete below the neutral axis, or the concrete below the neutral axis, okay, that is neglected. Okay, and it is assumed that only the reinforcement will take the tensile stress. Okay, so this is one assumption of working stress method. And this is how these are two pictures which show how it's basically showing this variation, the strain variation across. This is the stress variation. Similarly, you can also plot the strain variation across the depth. Okay, so this is this is 3. Yeah, so this is showing for, you have strain on the y-axis, and this is across the depth. So this is, say, top of the beam, say this is bottom of the beam, something like that. And depending on how much load is being applied, you can just see how the strains are varying. Okay, so you see that one side, I suppose this is the steel side because the strains are more. So you see that now here you have certain strains. You see that all of them are straight lines, more or less. So this is a straight line, this is a straight line, this is a straight line. These are all experimentally measured. Okay, these are experimentally measured. So I just taken the picture of those experimental results from the Park and Pauli book. Okay, so this is if you have a low eccentricity. Okay, meaning that low eccentricity means eccentricity means if you are applying load right through the middle, it's known as concentric. If it is not through the axis, if it's a little bit away from the axis, it's known as eccentric. Eccentricity causes moments. Anyway, those are all side details. Don't bother about it too much. So what I basically want to show from these two diagrams is, even in the case where there's a lot of eccentricity, even though it's slightly curved, even if you assume this curve as a straight line, it is not going to be too much wrong. Okay, even if you assume that this curve is as a straight line instead of a curve, even then you will not be getting too much of an error. Okay, so these two pictures show that linear strain assumption is reasonably correct because it appears almost linear, whether it is low eccentricity or high eccentricity. Okay, so now as I told you, you have this concrete beam, and here only one reinforcement rod is shown, but usually you will have 3 or 4. Okay, not usually you will not have less than 3 rods at the bottom of any RCC beam. Okay, so what is done is, whatever is above this dotted line is the neutral axis. Whatever is above it, you can say that the concrete is there. Below the neutral axis, where you're assuming it to be having a tensile stress, you assume that there is no concrete and only the steel rod is taking the section, taking the tensile stress. Okay, so top compression, bottom tension. That's why C and T. Okay, C and T. Now this is why I asked you a little bit a while ago. Do you remember this composite sections? Okay, so basically what is happening is the modular ratio, the ratio of the Young's modulus of concrete and ratio of the Young's modulus of steel. So divide this Young's modulus of steel by the Young's modulus of concrete. Okay, you will get a certain number. That number is known as modular ratio. Okay, usually it is given by the letter M. Here it is shown as N, but anyway, the common notation is the letter M. M is modular ratio. So that modular ratio times the area of the steel, if you multiply, it gives you an equivalent area of concrete. Okay, so for example, here we have concrete, here we have steel. Dealing with two different materials and analyzing is not it's not convenient. So even if you remember your mechanics of solids composite sections, what you do is you use one material, then convert the modulus of the other material into an equivalent value for the first material. So the same thing you do over here. You try to modify the area of steel to an equivalent area of concrete. So that is done by multiplying by the modular ratio. So you have some area of concrete, some area of steel in terms of concrete area. Okay, like that you have this. Then you have your stress distribution diagram. Okay, and this stress distribution diagram is linear, straight line. Okay. Now one question that I will ask here is, so you saw a few slides back the stress strain curve of concrete is the stress varies parabolically in concrete. Stress varies parabolically. However, here what I have shown is I am showing the stress, tensile stress, compressive stress and tensile stress to be varying linearly. How is this justified? Actually, in reality,
by this definition, it's like 1/3. So
which assumption?
like the first assumption is like WSM method is like one third of the is carried. Like.
So
So
you're
it has to
taking
be
only,
linear.
yeah, excellent, very good. Name
Prasad.
Ram Prasad.
Sure.
Okay, good. So that's the assumption that 1/3 or the linear part only is taken. So therefore, this you can drawing this as a straight line, assuming to be straight variation of stress is accepted. So in general, this is a stress. You can find out what the total force acting on this concrete block is. So that is given by C, total compressive force acting on this part. It's given by nothing but the area of this triangle times the breadth. Okay, so you get this. This can be assumed to act at the centroid of this triangle. Okay, acting at the centroid of this triangle. So that is compressive stress. The resultant compressive force rather. The resultant compressive force is acting at the centroid of this compressive stress block. So the word I'm using, please note those words. This is known as a stress block diagram. Stress block diagram. This is a compressive stress block. This, and for tension there will be no stress block because tension acts only across one single line. Okay, tension will be only along this line. So this is compressive stress block. This is tensile stress. And the difference, this tensile stress will act where the reinforcement is, because only the reinforcement is assumed to take the tensile stress. Concrete is not assumed to take any tensile stress. So the distance between these two opposite and parallel forces, it's given by JD. So if you have two equal and opposite forces separated by a distance, what is the name of the distance? What do you call that distance? What is the terminology for it? Distance between two equal and parallel forces.
Couple.
No, the two equal forces are known as couple. But the distance between them, have you used any name for them till now? Okay, maybe you have not used it. Right, C and T form a couple. The distance which makes that couple is known as lever arm. Lever arm. Lever arm. Okay, so these are terms which you need to know. Okay, now based on this, based on the area of concrete and the area of steel, you can actually define the failure of concrete in 3 different ways. Okay, the first one is known as a balanced failure. It is a failure in which both the concrete and steel reach their limits simultaneously. Okay, the percentage of steel which you have given over here. Okay, the percentage of steel which corresponds to a failure where both the concrete and steel will fail simultaneously. That is known as the balanced percentage. Okay, and this is an important limit, a percentage. Okay, because this is a dividing criterion which says which way a beam will fail. Okay, so if you look at this picture over here, yesterday when we were talking about the compressive test on concrete, what is the ultimate failure strain in bending compression for concrete seen yesterday? What is the ultimate strain that a concrete is assumed to reach in compression?
0.002.
That is axial compression. How about for bending compression? Slightly more. 0.00. You are right.
0.035.
0.0035, exactly correct. What's your name?
Nirbhay.
Huh?
Nirbhay.
Kirtiraj.
No sir, Nirbhay Singh.
Nirbhay Singh. Okay. Exactly. It's 0.0035. ACI code uses 0.003. That's why it's shown 0.003 here. Our IS 456 says 0.0035. Okay, so top it reaches that particular strain. Bottom it will reach a strain. Its bottom is steel, so easily you can find the strain. Just yield stress by Young's modulus of steel. That will give you the strain at yield. Okay, so that is pretty easy for steel. So if it's a balanced failure, concrete will reach 0.0035. Steel will also reach its yield strain, which is Fy by Es. Okay, which is this point. So in a balanced failure, this is your stress strain diagram. Okay, the bottom will be Fy by Es. Top will be 0.0035 for all failures. Okay. The second is known as a tension failure. Okay, and this happens when the stress in steel reaches the permissible stress in steel or the working stress of steel before the CEPC means C is for concrete, B for bending, C for compression. Concrete, bending, compression stress. Okay. So ST means steel. So wherever I'm using F means the actual stress which is there in that material. Sigma is used to denote the permissible or the working stress. Okay, the limit up to which you can allow it to reach. That is given by sigma. F is used to specify what is the actual stress existing in the material. Okay, so symbols are important. Each of them symbols tell you what it means. So this is the actual stress in steel. Working stress allowed in steel. This is the actual stress in concrete in bending compression. This is the working stress allowed in concrete in bending compression. So if it is a tension failure, FST will reach sigma ST before FCBC, which is the compression bending stress in concrete, reaches its working stress. Okay, so basically it says tension is going to steel is going to fail first in tension. So will this happen if there is more steel or if there is less steel? Steel is going to fail first under tension. When will this happen? Yeah, it will happen if steel is less in percentage or more in percentage. Simple, just very simple answer. It is going to fail
Yes.
first. It's way hard. If the steel is less, then it is going to fail first. So therefore, and further loading, what will happen if you, so it reaches sigma st, and if you continue to load it further, then the strain will keep increasing, because steel, you know, it is ductile. So even after it yields, it will still undergo some straining. That is the property of steel. It's not like concrete, where it, if tension happens, immediately it's going to crush in a brittle manner. It's not like that. Steel, even after it yields, it will continue to have a strain for some. It's known as ductility. Steel is a ductile material. So therefore, even after it fails, strain will keep increasing on further loading, along with some cracking. So if it is a tension failure, you know, the neutral axis will shift up, okay, towards the compression phase. So this is what is shown over here. Concrete always 0.003. This is tension failure, so therefore the strain in steel is going to be much more. So say that the strain in steel, this is for the balanced failure. For tension failure, the steel tension stress should be more. Tensile stress, strain should be more. So let me say it is over here. So when I join this and this, you see that the neutral axis has shifted to this position. It has gone, this is the balanced one, it has gone up now, because the strain in steel has increased. So just very gradually and patiently visualize all this. And finally, I mean, steel has already yielded. So steel will not keep yielding and yielding infinitely. At one particular stage, concrete will crush, and that is how the failure will happen. Now the other opposite of this is known as compression failure. So it is the opposite. If you give too much steel, then your steel strain will be very less as compared to the balanced failure. Your steel strain may be only this much. Okay. And however, before the steel strain reaches this point, so it is right now it is very less. As you continue to load it, before the strain in steel will reach the balance point, concrete will crush in failure in compression. Okay. So this is the difference. This will happen if there is excessive steel content. And here at least you have, steel has ductility. If you have under-reinforced, I mean, if you have more, if you have less steel, steel will, you know, it will undergo straining. It will be ductile. You can see that cracks are happening. Cracks will happen very slowly. You know, I mean, because steel is ductile, it will keep straining, and you can see that over a period of time, cracks may become wider. So this is a visible warning. You can look at it and say that, okay, that's a problem. Something has to be done to fix this. However, if you have this where steel content is excessive, steel will not fail first, concrete will fail first. Now when concrete fails first, concrete is brittle, it will not give you any warning, and the failure will be much more quicker, giving you no time to actually take any corrective measures. Okay, so this failure is one which is not wanted. This is a more preferred form of failure, tension failure. Okay, so now when I say that, and of course you see that here balanced, so this is the balance point. Tension failure, the neutral axis went up. For the compression failure, what has happened to the neutral axis?
It came down.
It has shifted down. So depending on the percentage of steel, your neutral axis will either go up or come down. Okay, and when I say too less steel or too much steel, it is with respect to this percentage known as balanced percentage of steel. If it is lesser than the balanced percentage, it is tension failure. If it is more than the balanced percentage, it will become compression failure. So these are very important concepts that you need to know. Similar concepts will be also told to you when dealing with the other philosophy. Okay. So these are some other provisions for your working stress method. You can just have a look at it. If you have your code book, you can either have a look at this code book. Probably after this class, sometime when you're free, just open the code book, look at Annex B. It gives you some provisions with regard to the permissible stresses or the working stresses in concrete and in steel. Okay, so you have different grades of concrete. You can see permissible stress in compression, direct compression, bending compression. Direct compression means it is it's not visible. This says sigma cc, concrete compression. This one says sigma cbc or concrete bending compression. And bond stresses. Okay, bond stress like the stress with the steel reinforcement bonding. So that's okay. This at least you don't need to bother for now. So as you see, look at the numbers. Okay, mainly look at all these numbers. M10 sigma CBC is 3. M15 sigma CBC is 5. M20 sigma CBC is 7. Likewise, M50 sigma CBC is 16. How did people get these numbers? How did these numbers come? For 10 it is 3, for 15 it is 5, for 20 it is 7, for 30 sigma CBC is 10. What is common about these numbers? How did these numbers come?
So like 1/3 value, sir. Approximately.
Okay, that's what you're taking, no? 1/3 value. Similarly, even for steel, you limit your stresses which can be used. So if your steel grade is 230, okay. Sorry, this is high strength steel. Okay, if your steel grade is Fe415, okay, meaning the yield stress of this grade of steel, actual yield stress of the grade of the steel is 415 Newton per millimeter square. But because you're using working stress method, once again here also they make a certain reduction to the stress that can be used, because high yield strength deformed bars, they are not like mild steel bars. I think I showed you a picture in last class. Mild steel bars will have a straight strain curve. They'll have a sharp yield point, then they'll go. High yield strength deformed bars, however, they will have a gradual yielding. They'll have a very gradual yielding. So there also they try to limit it to linear part of the stress strain curve. So why I'm saying this is something you may not be aware. Most of you in your mechanics of solids, you would have seen that mild steel. It's you would have seen mild steel, and you may be thinking that steel is always having a straight curve and then the yield plateau. It's not always like that. That is for mild steel. If you have this deformed bars or high yield strength bars, that will not be perfectly linear. That will be gradual yielding only. So for those bars also you have some reduction to take care of the linear part. So if you're using the bar in tension, you can use only 230 out of this 415. If you're using the bars in a column under axial compression, you can use only 190. Okay. So here also you see that there are some limitations placed on the stresses which can be used. So if I have time. So the other method, maybe just this part I'll just say. The other method is known as limit state method. Okay, so there's a big difference between working stress method and limit state method. Okay, so one thing is working stress method. It's a very simply derived method which says that looking at the material, only the material is targeted and said that the stress strain curve is quite uncertain. So we just limit it to 1/3 value, or for steel some other value, and use only the linear part, and other assumptions are made. Okay, so it is, I would not say it is unscientific, but it is more, what to say, it's the main purpose of that is simplicity. Okay. Now, however, whenever you do a design, you have two things to take care of. Okay, you have one part is the material. Okay, concrete, how the material properties of concrete or steel, whatever it is. The other part is what is the actual load that is going to come. Okay, so now among this material property and load, in your opinion, which is having more uncertainty? Is the material property more uncertain, or is the load more uncertain? In general, I didn't hear you.
Load, sir.
Load. Why do you say that?
Because sometimes there may be like natural hazards or impact rates.
Okay. Yeah, one of the reasons is those natural hazards, and even if without natural hazards, if there's a building, somebody changes the use of the building, load will change. For example, you have these days, a lot of the old cinema theaters, people change it to marriage halls. So change of application, change of use, it relates to a change of load also. Okay, so those kind of things as well. So load is more uncertain. So in limit state method, uncertainties are very rationally taken into account, and based on that only, the design process and the material, like for example, there you said directly 1/3 of the material strength can be used. Here it is not like that. Actually, certain rationally derived factors are used, and then based on that, the material strength and all is arrived. Similarly, also for the load, certain factors are used to take care of the uncertainties. So now here you have a normal distribution of two things. One is Q is, I suppose, a load. S is the resistance or the strength of the material. Okay, concrete or steel, whatever it is. Okay. And now you see two things over here. The one thing is the bottom says the value. Okay, like for example, resistance is some Newton per some kilonewtons or some newtons. Similarly, load also some newtons or some kilonewtons, whatever it may be. Here you have the frequency of the occurrence. Now what? So this is the curve which is related to the actual load which is present. Okay, this is the distribution of the load. The second curve is the distribution of the resistance or the strength of the material which is being used. Okay, so now in general, which would you want to be on the left? Which would you want to be on the right? Okay. This is the bottom x-axis shows the value of the load or the resistance. Both are the same unit, kilonewtons. Okay, just say both are kilonewtons. Now, which should be more, the resistance or the load?
Resistance.
Resistance should be more. Meaning that you would want this curve to be entirely outside this left side curve. Okay, you would want this. The ideal situation is the most. I will not say ideal. The safest situation is if this whole curve is starting only over here. But if it is like that, what is the disadvantage of having a situation where the curve of this resistance is entirely outside the curve of the load? What do you lose?
Expensive.
Expensive. Okay, it becomes expensive if you want everything to be very safe. Whenever you go to extreme safety, everything becomes expensive. Okay, so that also is not desirable. So there will be some bit of unsafety, but just ensure that that percentage is really less. Okay, so based on this, there are two limit states. Limit state means the word itself tells you the limit. Okay, the point where the limit of the material or the limit of the situation or the point where the particular material, either concrete or steel, reaches its limit. Okay, so that is known as a limit state. To be very to say it very simply. So there are two limit states. One is of collapse, one is of serviceability. There's a fundamental difference between both of this. It's described over here. Collapse, it deals with the strength and the stability of the structure under the maximum load. Okay, the term collapse itself means it is related to a failure of the structure itself. Which happens because the material strength has been exceeded by the load, and the material is no longer able to take it. It will either collapse or it will have stability issues. So that limit is known as limit state of collapse. Additionally, you also have another limit state which is not related to collapse. It's known as serviceability. Okay. Now serviceability deals with things which are less less extreme than collapse, and it deals with situations like excessive deflection, cracking, durability, fire resistance, etc. See, for example, say you have built a structure and you have built a roof. Say you have built a roof and it's built pretty strong. But the problem is it's not collapsing. Nothing is happening to it. It's low. The material and all is still within its strength. No problem. But say that it is deflecting too much. It's just deflecting, and whenever they say a heavy wind, it's just shaking or whatever in the roof. It's vibrating or something. So that's not a good situation. I mean, even if it is safe, people inside will think it is not safe because it is deflecting too much or vibrating or any other issues. So you may want to hang some lights or some fans or some other services. So if it deflects, all those things will get damaged. Those whatever fittings you have kept, those things may get damaged. And such kind of issues are there. Water may stagnate if it deflects downward. So these kind of issues are known as limit states of serviceability. So there are some limits placed on serviceability as well. So probably I'll stop with this today, and next week, if it is me, I will continue with this. But let us see what happens. Anyway, for B section, I will be continuing. This I'll close. Okay, stop the recording.